Okay, so as we said, the behavior of matter, most of the behavior that we look at has to do with how the electrons are behaving, because the nucleus is held together by the strong force. And there is a chapter later on in the textbook in General Chemistry 2, you'll talk a lot about changes that can occur in the nucleus. If you don't have the right number of protons and neutrons, it becomes unstable. But most of the matter around us has reached a stable state. That's why it's existed so long. And most of the matter around us has a stable number of protons and neutrons in the nucleus. And that force holding that together is strong. So what we want to know is what's happening with the electrons and how do they behave, because that explains the vast majority of physical and chemical phenomena that we observe in nature. So in order to do that, what we'll see in this chapter is we're going to interact light with matter and see how that affects the electrons. So we have to understand a little bit of basic stuff about light so that we can characterize that and see when it affects the electrons, if that can give us some information about what the electrons are doing. So we know light is also known as the electromagnetic spectrum. So light has an electrical and a magnetic component, and really it's just a form of energy. So we can transfer energy from one location to another with light. We can transfer all the different forms of energy we've talked about into light and vice versa. So you could take potential energy, convert that into light. We could take light and convert it into potential energy. We could take kinetic energy and convert that into light and vice versa. So we know that there's all types of different energy conversions that are possible. When we look at light, we know on the spectrum that a short wavelength is higher in energy. So the energy that you experience if you're getting struck by light depends on how many kind of packets of energy are packed in there, or photons of energy are packed in there. So if I'm standing here and I get hit by some light, we want to think of the light as traveling in waves. And if that light is hitting me, each wave carries a packet of energy. So I could think of these waves as carrying packets of energy. Right? So if I get hit by a wavelength of light that has a long wavelength, like radio waves, which is what our cell phones all communicate with, and that's also like television broadcast. If I get hit by radio waves, or even microwaves, which are not quite as low energy as radio waves, or infrared, or visible light, none of that really is very dangerous to me. So microwaves, we know, heat up our food, and so obviously that could be dangerous. If you get hit by a lot of microwaves, the microwaves cause the molecules, especially if it's tuned to the right specific type of wavelength for a microwave, that will cause your molecules to rotate around, and that rotation is molecular motion, and that can cause a temperature increase. So that any form of energy that causes too much of a temperature increase is dangerous. But the waves themselves are not dangerous. There would be the temperature increase that's a result of those waves that's dangerous. But the lower energy forms of light are not dangerous because there's only a few packets of energy, and they're all spread out because the wavelengths are long and the wavelengths are spread out. If I were to get hit by something more on the dangerous end here, gamma rays and X-rays being the most dangerous, now I'm talking about waves that are much closer together. So if I get hit by that, now I've got a lot more packets hitting me in a specific period of time because the packets are very tightly packed close to one another. Okay, so that's one way to think about the relationship between energy and wavelength. And so what is frequency? I assume everyone here knows what the word frequent means, or frequently. So frequency is pretty much the same thing. It just means how frequently are these waves traveling through a given point. Right? So if we think about the unit for wavelength, that makes sense. It's a distance, right? It could be meters, it could be centimeters, it could be inches, it could be nanometers. Usually it's nanometers, but those all measure distances, right? So as we said, the wavelength is a distance between waves. So long wavelengths are low energy, shorter wavelengths are higher in energy because we have more packets of energy packed into a given amount of space. Frequency has a unit that you might not be as familiar with conceptually, but a hertz is just a 1 over second. Also a weird unit to imagine. Obviously you know what the unit second means, right? That's a period of time. But what's the unit per second, or 1 over second? Usually that doesn't make sense unless you have some unit on top as well. So there actually is a unit on top of that, and it's actually waves per second. That makes more sense. If I'm standing there getting hit by that light, the number of waves of light that hit me per second is the frequency, or that's how frequently I'm getting hit by packets of energy. Okay, so hopefully that clarifies that concept conceptually for you as well. So the shorter wavelengths, the higher the frequency. The more often I'm getting hit by packets if the packets are packed together into shorter wavelengths, right? So shorter wavelength, I get hit by more waves, or I'm more frequently getting hit by waves. The frequency of that wave is higher, and I'm getting hit by more energy, so the energy is higher. Right, so we're going to talk about, now we have a little bit of background about light. We also know that amplitude has to do with how tall the waves are. That's what the amplitude is. So if I'm looking at this red wave here and I compared it to one with a higher amplitude, it would look more like this. So that black one that I put on top of the red one there, it has the same wavelength, right? Because the distance between waves here is the same as the distance between waves here. So those two waves have the same energy. Okay, the energy, they carry the same number of packets of energy since the waves are the same distance apart. They have the same frequency because the waves are the same distance apart. Right, so this is a higher energy because the wavelength is shorter and the waves are packed closer together. Amplitude is not related to the energy. Amplitude is related to the intensity. Okay? So when you think about light traveling, there's kind of two different ways you can think about it, and light has this kind of dual property of both particle and wave. And it's good to have a mental picture of both of those, because sometimes in some applications light will behave more like a wave, sometimes it will behave more like a particle. And whatever's more convenient for you conceptually to remember how light behaves is probably a good way to think of it. So when we think about the energy and the frequency, it's helpful to think of it as waves carrying packets of energy. When I think about the amplitude, that's not as obvious conceptually how that relates to intensity. So you can remember that the taller waves are more intense light, or you could also think of it as the taller waves having more photons. So you're getting hit by more photons. But the photons themselves, these kind of like particles of light, the photons have the same amount of energy if the wavelengths are the same. It's just if the amplitude is greater, you get more of those photons. Right? So if I'm getting hit by visible light, I could turn on the lights in here as bright as I want. It's not going to give me skin cancer. Right? Because visible light is in an area of the spectrum where the wavelengths are long enough that it's not very high energy light. Even if I turn it on really bright and I have to put sunglasses on or something, that's going to be high amplitude, but it's not going to be a high energy light. And if I go and expose myself to a bunch of X-rays, then those X-rays have a lot more energy. That's going to start affecting in a much more significant way the molecules in my body, and it's going to be cancer causing, or even it might kill me even faster if I get exposed to too much of it. Okay, so it's the wavelength and frequency that determine the energy of the light. The amplitude is just how bright that light is. So is it dim or is it bright? And so you can think of dim or bright visible light is not dangerous either way. So that all that visible light has the same energy regardless of how bright it is. Any questions about that? Okay, so light travels at a constant speed, assuming it's in a vacuum. And that's the fastest speed for anything that we know of. And the speed of light is equal to the wavelength times the frequency. So I'm not going to expect you to be using this formula to do calculations, even though it's relatively straightforward. As far as light goes, we're more concerned in here with the conceptual aspect of that and how it interacts with the electrons and what that tells us about the behavior of electrons and how that explains how matter exists. That's what we're more concerned with than I'm not as concerned with you converting frequencies into wavelengths. Okay, but that is the relationship. So the key thing here, though, is because light travels at a constant speed, that enables us to make these relationships between frequency and wavelength and energy. Right? So let's imagine. So we already kind of talked about that. Let's go here first, and we'll come back to look at those other ones. So we just said that the energy is greater if I have a higher frequency. Right? Conceptually, hopefully that makes sense. Because if you're standing there getting hit, and the wavelengths are short, you're getting hit by a lot more packets or wavelengths or waves of energy in a short period of time. But how would that be different if the speed of light were not constant? So the first question here we just answered. Should a wave with a short wavelength have a high or low frequency? I'm sorry, high or low energy? If it has a shorter wavelength, it should have a higher energy. Right? Because you have more packets of energy packed in with all those waves packed close together with the short wavelength. So if the speed of light were not constant, would the relationship between wavelength and energy still be the same? Would it be possible to have a longer wavelength with a higher energy if the speed were not constant? So if I'm standing here, what we said was, if the one with the long wavelength and the energy packets are spread out, that hits me, that's not much energy, right? But if I have a much shorter wavelength, oh, that's terrible. Get really lazy on that one. Let's try that again. So now I've got a lot more packets of energy, right? So we said when that one's hitting me, that's a higher energy. But that's assuming that they're traveling at the same speed, which they are because the speed of light is constant. So it doesn't matter what the wavelength is, the light is always traveling at the same speed. If it weren't, which is not correct, but I'm just saying for the sake of argument, if they weren't traveling at the same speed, this one could potentially be traveling through space flying at me much faster, and this one might be going much slower. In that case, the one with the longer wavelength could be supplying or providing more packets of energy in a given period of time. It could also have a greater frequency. Yes?
Like, what's traveling at the same speed? Is that the packets of energy, or is that like the crest of the wave traveling at the same speed? Unlike the top of the
Right. That's a good question. So if I took, let's just say I picked a point on this wave and the same point on this wave, and I wanted at the time how long it would take for this point to travel through space and get to this point here. It would take the same amount of time as for this point to travel to the same distance. So the actual speed in miles per hour, or the time it takes to get from point A to point B for any wavelength, is always going to be the same. So it doesn't mean that you have the same number of waves traveling through, right? Good. So if they were traveling at different speeds, if this one were traveling 90 miles per hour and this one were traveling 1 mile per hour, 1 mile per hour, then the top one would be higher in energy, and it would have a higher frequency, because I would get more waves per hour. All right, but we know that that's not true. So I just wanted to point that out as a conceptual way. So hopefully you understand that the waves are traveling through space, and that they carry packets of energy that are spaced apart based on their wavelength. More packets of energy, higher energy form of light. So we know that waves, we can think of waves then as particles, because the packets are like particles, or they're called photons. It's like particles of energy. And we know that those travel through space, so we can hopefully you can at least make a mental picture of what that looks like. But light also behaves as waves. It's not just particles, and we know that because of the constructive and destructive interference that waves can undergo. Right? So one experience you probably already have with this constructive and destructive interference, or at least a way you could think about this conceptually, would be to think about water displacement. Right? So we know if you have, let's say you have a pool here, and it's got water in it, and you're here, and you jump in the pool, that will create a wave, right? You'll displace some of that water, and when you jump in, the water is going to be pushed up, and you'll get a wave that travels across the surface of the water, right? So the interference between waves occurs when you have one wave traveling and another wave also traveling. Those two waves could be traveling on the water in opposite directions and cancel one another out, or depending on the timing of when you jump in the water, they could add together. So if I have someone standing on the other side, and they jump in here as this first wave is traveling across, and they create another wave, and those two waves are traveling toward one another, the waves will collide and destructively interfere. The force of one wave moving in one way in one direction will cancel out the other wave. Right? So that's called destructive interference. And that occurs with all waves, not just with waves, standing waves on the surface of water, but also with waves of light. But waves can also constructively interfere. Okay, so if I do this a little bit differently, if I allow this first wave, to travel all the way down here and hit the end, and then it starts to go back in the other direction, if I jump in then, I'll create a second wave that adds to the first wave. And I could actually keep doing that and create like a huge wave. Eventually, over time, the wave grows and grows and grows. If I keep jumping in at just the right moment and displacing water to add to the water that's already been displaced, I can create a huge wave in a pool. My high school physics teacher had us do that on one day in physics, and it was a lot of fun jumping in and out of the pool. It got really tiring for a while, but we created this huge wave that traveled the whole length of the pool. It was actually pretty cool. So that's called constructive interference, when the waves add together. And so we know that light isn't just a particle of energy flying through space. It's not just a packet of energy. It travels in waves, because waves of light can also undergo constructive and destructive interference, the way particles don't actually behave. And so if you have light traveling through a small slit, and then you add another barrier with two more small slits, and the light travels through there, it affects the angles that the light is traveling. And you actually, if you shine a flashlight through that type of setup, you will get a pattern of dark and light areas on the whatever background you're shining that flashlight on, because of the destructive interference where the light waves cancel, and the constructive or light areas interference coming together in those other areas. Yes?
And like light waves cancel with X-rays or just other light waves?
That's a good question. So your question is, if two forms of light come together with different wavelengths, would they still constructively and destructively interfere? Yeah, they would, but I think the pattern you would get would be much less. It wouldn't be an ordered pattern like the pattern here. It would be much different, much more different. Yeah. If the wavelengths are too different, then there might be less interference between them. Yeah, that's also a possibility. So the terms in phase or out of phase just refer to, in phase means the waves, one wave is coming and another wave adds with it, and that gives you the constructive interference. And out of phase means they're not adding together, they're just coming at opposite times, so they cancel one another out.